Welcome to our unit over electrons and atoms. A calculator and your reference chart will be useful as you watch this video and take notes. In the early 20th century, a new atomic model evolved as a result of investigations into the absorption and emission of light by matter. These studies revealed the relationship between light and an atom's electrons. This new understanding led directly to a revolutionary view of the nature of energy, matter, and atomic structure. We will start by taking a look at the properties of light. Light can behave as waves or as particles. Let's look at the wave nature of light. Light can travel through space as a wave. Waves have three primary characteristics. The wavelength, lambda, is the symbol, the frequency v, and the speed c. Wavelength is the distance between corresponding points on adjacent waves. The unit for wavelength is a distance unit. The symbol is lambda, and it is measured in meters. So the wavelength could go from a crest to another crest. The crest is the highest point in the wave, or it could go from a trough to another trough. The trough is the lowest point in a wave. The frequency v is the number of wave cycles or successive crests or troughs that pass a given point per unit time. The symbol is v, and it is measured in cycles per second. The unit can be the hertz, or it could be second to the power of -1, or 1 over seconds. All these units are equivalent, and you need to be familiar with all of them. The diagram here shows a wave with high frequency at the top, where you can see that the wavelength is very short, and a wave with low frequency at the bottom, where you can see that the wavelength is much longer. The speed of light, c, is a constant for all forms of light or electromagnetic radiation. The symbol is c, and it is 3.00 times 10 to the 8 meters per second. This will be given to you on your formula chart, so you do not have to memorize it. Let's look at the electromagnetic spectrum. Visible light is a kind of electromagnetic radiation, which is a form of energy that exhibits wave-like behavior as it travels through space. There are other kinds of electromagnetic radiation, and these include gamma rays, X-rays, ultraviolet and infrared light, microwaves, and radio waves. Together, they all form the electromagnetic spectrum. This chart down here will be given to you, so you do not have to memorize it. You can take a look at the chart and see that as we have a high frequency wave on the gamma ray side, the wavelength is very short. On the other hand, where we have a low frequency wave on the radio wave side, the wavelength is very long. So here we have increasing frequency towards gamma rays, and down we have the increasing wavelength towards the radio wave. So we can see that wavelength and frequency have an inverse relationship. Note also that all these forms of electromagnetic radiation will travel at exactly the same speed, which is the speed of light, 3.00 times 10 to the 8 meters per second. The speed of light, c, the wavelength, and the frequency are related by the formula speed of light equals wavelength times frequency, or c equals lambda times v. The frequency and the wavelength have an inverse relationship, as we discussed in the previous slide. Let's do an example calculation using our equation. The equation will be given to you on your formula chart also. What is the frequency of radiation with a wavelength of 3.82 times 10 to the -7 meters, and in what part of the electromagnetic spectrum does this radiation fall? As usual, we start with our equation. C equals lambda, the wavelength, times v, the frequency. We know that the value for c is 3.00 times 10 to the 8 equals the wavelength, which is lambda, is 3.82 times 10 to the -7 and we don't have the frequency V. So we divide by 3.82 times 10 to the negative 7, and we divide by the same thing on the other side, times 10 to the negative 7, and that gives us 7.8534 times 10 to the 9. Now we look at our significant figures. We have 3 over here, and we have 3 sig figs in our value for C. So we want 3 sig figs in our answer. So 7.85 times 10 to the power of 9. The unit for frequency is hertz, or it could be seconds to the power of -1, or 1 over seconds. All of these 3 would be acceptable. Now, which part of the electromagnetic spectrum does this fall in? So we had a wavelength of 3.82 times 10 to the negative 7. So I go find that on my chart. Wavelength numbers are at the bottom. And I find 10 to the negative 7, which will fall somewhere here in the visible light spectrum. So it is in the visible part of the electromagnetic spectrum. Now let's look at the particle nature of light. Not all properties of light can be explained by the wave model. So Max Planck and Albert Einstein refined our understanding of light to include its particle nature. Light can be described as a stream of particles or bundles of energy called photons. The details of the particle nature of light cannot be discussed in this class, but we will highlight the relationship between energy and frequency of light. So Planck and Einstein proposed the following relationship. The energy of a photon of light and its frequency are related by the formula energy equal Planck's constant times the frequency. And there is the formula over here. E is the symbol for energy. H is the Planck's constant, which is 6.626 times 10 to the negative 34 joules second. Again, this is given to you on your formula chart, so you do not have to memorize it. The unit for energy is joules. Energy and frequency, note, have a direct relationship. When energy goes up, the frequency goes up, and vice versa. So let's do a calculation using this equation. How much energy does a photon of light with frequency 4.2 times 10 to the 8 hertz have? And what part of the electromagnetic spectrum does this fall in? So again, we start with our equation. E equals H, Planck's constant, times V, which is the frequency. Then we plug in our numbers. So E equals 6.626 times 10 to the negative 34 multiplied by the frequency, which is 4.2 times 10 to the 8. Plug into your calculator and we get 2.7829 times 10 to the negative 15. We look at sig figs. We have 2 sig figs over here and we have 4 sig figs for our H. So we want 2 sig figs. So we get 2.78 times 10 to the negative 5. And the unit for energy is joules, abbreviated J. What part of the electromagnetic spectrum is this in? We look at our frequency, which was 4.2 times 10 to the 8. So the frequency numbers are at the top here on the chart. I go look for 10 to the power of 8. Here it is over here. And all this is all radio waves. So radio waves is where it falls in. We do not yet have a relationship between energy and wavelength, but we can combine the 2 previous equations, which was C equals lambda wavelength times frequency V, and E, energy, equals H, Planck's constant times frequency V, and obtain the above equation, which is the energy of the photon equals H times C over lambda. Again, this equation is given to you in your formula chart. So let's do an example calculation with this equation. How much energy does a photon of light with wavelength 6.25 times 10 to the power 4 centimeters have? Now we have to be careful because our wavelength to plug into the equation needs to be in meters. So the first thing we have to do is convert our centimeters to meters. So we have 6.25 times 10 to the 4 centimeters. And I do my dimensional analysis with my equality between centimeters and meters. And we have 100 centimeters is 1 meter. And I get 625 meters. Now I have my wavelength in meters. So I write my equation. E equals hc over lambda, which is the wavelength. And I can plug in my numbers. So I have h as Planck's constant, 6.626 times 10 to the negative 34, multiplied by c, which is the speed of light, 3.00 times 10 to the 8, divided by the wavelength, which is 625 meters. I plug this into my calculator and I get 3.18048 times 10 to the negative 28. I look at sig figs. I have 3 sig figs over here for my wavelength. I have 4 sig figs for H, 3 sig figs for C, so I want 3 sig figs. So 3.18 times 10 to the negative 28, and the unit for energy is joules. Now, all atoms absorb and emit light or electromagnetic radiation when excited by a source of energy such as heat. Atoms of a particular element will emit light in a unique, distinct pattern called an emission spectrum. And emission spectra are like fingerprints that can be used to identify elements. You can see on the picture to the right that all these different elements, such as hydrogen, helium, neon, sodium, and mercury, have a different distinctive pattern for their emission spectra. Emission spectra correspond to the movement of electrons between energy levels. So electrons in an atom absorb energy in small specific packets called quanta. And a quantum of energy is the minimum quantity of energy needed to move an electron from the lowest possible energy level, which is called the ground state, to a higher energy level, which is called an excited state. When an excited electron falls back to its ground state energy level, light or electromagnetic radiation is emitted in the form of photons. So scientists had established that light could behave as both a wave and a particle. So they wondered if electrons, which were known as particles, could also have a dual wave-particle nature. And the answer was yes. The work of several scientists such as de Broglie, Heisenberg, and Schrödinger laid the foundation for the modern quantum theory and the quantum mechanical model of the atom, which you learned in the previous unit. So the idea of electrons having a dual wave and particle nature really troubled scientists. If electrons are both particles and waves, then where are they in the atom? So Heisenberg came up with a principle called the Heisenberg uncertainty principle, which states that it is impossible to determine simultaneously both the position and velocity of an electron or any other particle. So because measuring the position of an electron actually changes its position, there is always a basic uncertainty in trying to locate an electron, and so its exact position cannot be found. This discovery is what made the Bohr model flawed, because the Bohr model placed electrons in exact locations in orbits around the nucleus, and that contradicted the Heisenberg uncertainty principle. On the other hand, in the quantum mechanical model, an orbital in the electron cloud represents a region that is a probable location for an electron. So this was in line with the Heisenberg uncertainty principle. This concludes our video. I hope you have taken good notes. Come to class prepared with your questions.